Well, hello everybody, this is Dave, and we're going to finish up our lessons on exploring data by taking a look at how we can actually take quantitative data and turn them into numbers that can be useful in a statistical sense. We've already gone through lessons that deal with the visual, so if you haven't looked at those yet, I'd definitely go there. But otherwise, we're going to go ahead and now crunch some numbers. Now, in a previous lesson, we talked about this idea of finding the center of a distribution. And depending upon the shape of the distribution, you're going to use a different center measurement. The first measurement we'll talk about is the mean. Now, you've all calculated these if you've ever calculated an average of any kind, and that's simply taking the sum of all the data points and dividing it by the total count of the data points. So if we have 20 values, we add up all the values and divide it by 20. And so this is not a new calculation, but what is going to be very important to recognize is the notation that we use. You notice that the mean is represented by an x with a bar above it, which we'll just call x bar. You're going to see in statistics that we have a lot of quantities where we label them as x bar or p hat, and we're going to have what I call decorations above the letters. At the same time, we're going to have other quantities that we label according to Greek letters, and those are going to mean something different to the study of interest. So it's important to get used to this notation now because moving forward, we're going to see this notation matter a whole lot more. Now at the bottom, you can see an equation here that is summarized a little more than the equation in the green box because we're using the Greek letter sigma. And if you've never run into this before, this just means we're doing the summation of all the x values to whatever index I we choose. So if we have 20 values in a data set, then we would take the sum until we get to the 20th number in that data set. And so I don't want you to get confused by that equation. I want you to recognize that that equation there is equivalent to the equation in the green box where we show that it's just x1 plus x2 all the way up to the final x value in your data set. Another quantity that we can use to measure the center is known as the median. And if you've ever been on a street before, you know that concrete thing that's right smack dab in the middle of a street? Well, that is called a median. And so it's pretty easy to recognize that median represents the middle of a distribution. And so to find the middle of a distribution, it's actually a little more straightforward than finding the average. We simply have to count from the outside in. And so the rules that we've listed here are going to be the rules that you're always going to apply. The first step is going to be taking your data set and arranging it from lowest to highest. And then you're simply going to count from the outside in until you reach the middle number. If we don't have a middle number and we actually get stuck on two numbers, and that's going to be the case if we have an even data set, then what you'll do is actually take the average of those two numbers, and that value will be the median. So whereas with the mean, we could end up with decimal values a lot, with the median, it's almost always going to be an integer, with the exception of having this case where you have to take the average of the values. So let's try and use these measures of center. We have here a data set that comes from the commuting times of 20 randomly selected New York workers. And you'll notice that they're not arranged in any particular way yet, but we'll see how to do that once we get to finding the median. To find the average, it's pretty straightforward. We simply add up all the values, which in this case is going to be 10 plus 30 all the way up to 40 plus 45, and we're going to divide it by the total number of values, which in this case is 20. And this gives us an answer of 31.25 minutes. Now, when you're showing work in statistics, one of the things you are going to hear me preach about a lot in my lessons is demonstration of understanding. And everybody in this lesson is going to be able to actually calculate the average, and you'll find out that the calculator does it for you very quickly using one var stats. That's not the point. Statistics isn't necessarily about finding the number, it's about the methods by which you found that number. So showing the work, and you'll notice that I use 3 dots to represent that, yes, I'm going to continue doing this all the way to the end. This is a great way to demonstrate that you understand what the average is, and most importantly, you've put appropriate units on the value that once you've calculated it, which is really important because in statistics, values have context. So please make sure that you're always representing the values according to the appropriate units. Now, if we want to find the median of this, what we can do is we can look at a stem plot of the data set. And if you notice now, what we can do is we can start at 0.5 and we can start at 8.5. And basically, you put your left finger on the 0.5 and your right finger on the 8.5, and you simply count in one at a time on each side so that you're coming in equally until you get right to the center. And in this case, because we end up at a 0 and a 5, so 20 and 25, the median value is going to be smack dab in the middle of that. So to find the median in this case, because it's an even number of data points, you simply have to take the average of these two values to get 22.5 minutes. Now it's important to recognize that we only found the average of the two values because it was an even data set. If you have an odd number of data points, then you can simply find that middle number and quote it exactly. Remember again, we have some units here. Make sure you show them every single time. In a previous lesson, we started talking about how to describe a distribution. And in doing so, we came up with the acronym of SOX to tell us about the 4 points that we should always look for. Specifically, those mean shape, outliers, center, and spread. Remember, with shape, we would talk about it in terms of being symmetric or skewed left or right. When it comes to the center, we just went through the two calculations that best describe the center of a distribution, whether it be the median or the mean. Well, with spread, we also have two quantities we can use, and the first one is known as the IQR, or the interquartile range. And the word quartile is important because we are literally taking the data set and we're splitting it up into quarters. And then we're going to find the difference between the first quartile and the third quartile. So to find quartiles, it's very similar to how you find the medians, because the first thing we do is we take the data set and we arrange it from lowest to highest numerically. From there, we find the median. Once we find the median, we now know where the data set cuts in half. Now all we need to do is take the first half and find the median of that. That's going to be called our first quartile. And then we're going to take the second half of the data set and we're going to find the middle of that, and that's going to be our third quartile. The IQR is going to be defined then as the difference between the third quartile and the first quartile. So to do this, it's better to just get your hands dirty and actually play with a data set. So we go back to the 20 New Yorkers values here. And the first thing we have to do is rearrange it according to numerical order. So again, from lowest to highest numerically. Now don't worry about the doubles and triples because again, to find the median, all we do is we count from the outside in. So if you put your finger on the 5 and the finger on the 85, and you count in one at a time each side, you're going to end up hitting 20 and 25. Remember, we found the average of that to figure out that the median was 22.5. But now look what else we can do. We have the median if we simply do the same process again. Put your fingers on the data points and start counting in until you get to the middle. And what you end up with is the first quartile equal to 15. We can do the exact same thing on the second half of the data set and put our fingers on the lowest number and highest number and count your way in until you get to 40 and 45. Well, we take the average of those as we always would, and we would get a third quartile of 42.5. So a common question that's asked in this case is, if you're finding the median and it happens to be an average, do I count from there or do I count from the data points? And the answer is you count from the data points themselves. So what do? I simply, for the first quartile, again, I put my finger on 5 and I put my finger on 20. And that should be able to count in to get to those shaded regions there in red. And that's important because when it's an odd data set, then you have to do it exactly the same way, but now you will actually have the median to include. To find the IQR now, we simply take the values and we subtract them and make sure you recognize the fact that it is still in units of minutes. So the IQR is going to be 27.5 minutes. And what's important in statistics is always understanding what the values actually mean. And so the interpretation of the IQR is literally the range of the middle half of travel times for the New Yorkers in the sample is 27.5 minutes. And one of the things you're going to run into a lot in statistics are scripts. Things that when we're talking about certain quantities like the IQR or the median or the mean, that you use the appropriate language to describe these things. Because if you don't use the right wording, then you might be talking about a different type of quantity, and that's not going to show a demonstration of understanding, and that's going to cost you not only confusion, but it's also going to cost you a little credit on any assessment you do. We have another way of measuring the spread, and it's called the standard deviation. And I'm sure a lot of you in your educational lives have heard of this before, but you may not necessarily know what it represents. To calculate the standard deviation, we first and foremost have to calculate the mean. So on the bottom dot plot there, we can find that the mean is going to be equal to 5. How did I do that? Well, I can look at the dot plot, and I know that I have a data point of 1 and 3. I have 3 4s, I have a 5, I have a 7, 8, and 9. So being able to take a dot plot like this and extract the values from it, I should be able to very quickly then find the average value. But now I want to calculate the deviations from that mean. So here's an example of a deviation. If my mean is 5 and I want to get out to the value 1, I take the observed value and I subtract the mean from it, and I get a value of -4. You can think of this in a number line sense, as that means that it's a value of 4 to the left. The exact same process can be used to find a deviation of, say, from 8, because we do the observed value, which is 8, minus the mean, which is 5, and we get a value of 3. The fact it's positive lets us know that it is a deviation to the right of the mean. If we continue this calculation for all of the data points, we can actually begin to create what we're calling the standard deviation. The first thing we would do is actually take those deviations and square them. And then we can find the average squared deviation by taking the sum of them and dividing them by n-1. The reason for n-1 is fairly straightforward. It is a limitation on the mathematical equation itself. If you don't have more than one data point, you can't take the standard deviation because there would be no deviation from that data point. So you need a minimum of 2 data points for there to be a deviation at all. And that's why it's n-1 instead of just n. So if we take the sum of the squares and we divide it by n-1, what we get is the average squared deviation. This is also known as the variance. And this is an important quantity in statistics, and you're going to want to make sure that we know the difference between the variance and this commonly used term, which is the standard deviation. And the standard deviation is simply the square root of the variance, which in our case is going to be 2.55. Now, because we're talking about the number of pets in this case, there are no units to it. So to generalize these findings, the standard deviation of a sample labeled as S sub x is the measure of the average distance from the observations to the mean. The variance is just the average squared distance. And we have these equations here, and it's important to recognize that I said specifically that this is the standard deviation of the sample. What you're going to find out again is in exactly the same language that I used to describe the mean, you will have letters to describe a sample standard deviation, and you will have different Greek letters to describe the standard deviation of what we'll call the population. So it's important again to get used to this notation now. Now, if you look at these equations, they look pretty hefty, but again, we're using this summation notation, and again, the only difference between the standard deviation and the variance is the standard deviation is the square root of the variance. This is a nice thing to remember because multiple choice questions very often want to ask you about things like standard deviation and variance, and they don't always give you the right quantity, and you'll need to either square the standard deviation to get the variance or square root the variance to get the standard deviation. Either way we go here, the square root of 1 over n-1 times the sum of the observed value minus the average value, all that squared, that's going to be how we always calculate the standard deviation. Now your calculator will do this just like it did with the average, but if you use the 1var stats command in your TI calculator, be very careful. Because in using that, what you've done is you've put a list into your calculator. And when it calculates it, it actually lists 2 possible standard deviations. One is labeled with a sigma, a lowercase sigma, not this e. It actually looks like a 9 that's been pushed on the side. And then you have an S sub x, which represents exactly what we have listed here, which is the standard deviation of the sample. It's important that when you use the calculator, no matter what the context is of your problem, that you're going to use S sub x as the calculated standard deviation for that data set. So we've taken a look at SOCs in terms of shape, center, and spread. What we haven't done yet is come up with a statistical method by which we can identify outliers. Until now, the best we could do is take a look at a graph, and if we see a data point that is a little far away from the distribution, we can say that that's a potential outlier. It's important that unless you use the test we're about to learn, I would strongly encourage you to only use weak language. This is a potential outlier. Don't say that it absolutely is an outlier, because unless you have statistical evidence to back that up, the best you can say is a potential. But what we can do is calculate something called the 1.5 IQR. And the way this works is simple. We have the IQR. And if we multiply the IQR by 1.5 and then add that value below and above the IQR, what we're saying is that any values outside of that is statistically going to be considered an outlier. Now, there's an awesome proof for why this is true, and I encourage you to Google it and take a closer look. But for the sake of this course, it's beyond the scope that we need to talk about. For now, if we go back to the New York travel time data, we know that the IQR was 27.5 minutes. So if we go 1.5 times that value, we get 41.25. Now here's the trick. You take your quartiles and you either add or subtract it according to if we're trying to stretch it below the quartile or above the quartile. And you can imagine just grabbing on to the first quartile and third quartile and literally stretching it away. So what do we do then? We take the first quartile and we subtract the 1.5 IQR because we are trying to move that lower bound even lower. With our third quartile, now we're going to add the 1.5 IQR because we are going to take that upper limit and we're going to move it even farther. And now what we can do is we can say that any values that are lower than negative 26.25 minutes or higher than 83.75 minutes, we're going to consider that an outlier. Well, it makes sense that we have no values below negative 26.25 because we're talking about commute times. But if we're talking above, we can see from the stem plot here that 85 is a value that is actually higher than 83.75. And so 85 would be considered the one outlier of this data set. So the 1.5 IQR test is essential if you want to have statistical evidence to support your claim that something is considered an outlier. We now have a lot of different quantities to talk about. We have means, we have medians, we have quartiles. All of these quantities now are going to be useful in some way depending upon the statistical analysis we're trying to do. One of the best tools that you're going to have to use now is known as the 5-number summary. And the 5-number summary is basically the minimum, the first quartile, the median, the third quartile, and the maximum value for any given data set. It's important to understand this order because this is the way that the 5-number summary is always written. So we've gone through how to find quartiles, we've gone through how to find medians, we understand how to find minimum and maximum because just look at your data set and you should be able to identify them pretty quickly. So this tool here is something that you're going to want to make sure you can read and extract the necessary information you need to move forward in your statistical analysis. One of the best plots that you'll ever learn in statistics is known as a box plot. And this is directly related to the 5-number summary because we can actually use those numbers to create the box plot. Now, why is a box plot so useful? Simple. It is easy to draw. You can make it quickly, and from that you can understand a little more about center, about spread, about shape, and even outliers. If you have a TI calculator, I encourage you strongly to learn how to make these plots with it because it's one of the best tools to use instantly to figure out exactly what you're tackling with a given statistical scenario. The description for creating a box plot is right here. The first thing you do is create a box. It is typically going to be a long rectangle, not too long, but a rectangle from which the left edge of the rectangle is going to be the first quartile and the right edge of the rectangle is going to be the third quartile. You're then going to draw a line somewhere in the box, and that box is going to represent the median. Obviously, we're going to need some sort of horizontal scale to determine where these values are. They don't just simply get labeled onto some random box. So we'll show you how to do that in a minute. From there, now we get to create the whiskers. A box plot is also known as a box and whisker plot because from the box you create these lines horizontal outwards towards the minimum and maximum. Now, one of the key statements here is that so long as a value is not determined to be an outlier, you're going to take those whiskers and you're going to draw them all the way out to the values, and then you're going to draw little vertical lines just to represent basically a cat's whisker. An outlier is going to be labeled with a star. Now, your calculators, again, are very good at this, and there's actually 2 box plots that a TI calculator can make. You want to pick the one that looks like a TIE fighter from Star Wars shooting something out because there's this little dot to the right of it, and that's the one you're going to want to use. So let's go ahead and readdress our New York travel time data set. We had our data set, and from it we rearranged it and we found our quartiles. Well, that's fantastic. We're going to use these now to create the box plot by first making a horizontal axis that has an appropriate scale for the data set. This is going to be important to understand how to create, because you don't want to just always make it the same scale. You want to make it a scale that's appropriate to your data set, especially if you have multiple data sets to have to graph on the same scale. You're going to want to make the scale appropriate so that all the box plots can be stacked one on top of another for the means of comparison. You'll see questions like that down the road. From here now, we can identify the rest of our numbers. Remember, we knew the median, the first and third quartile. Well, the minimum value here is 5, and the maximum value was 85. But you'll remember that we've identified 85 as an outlier. So when we create our box plot, here's how it works. First and foremost, we draw a box. And on that box, we're going to have vertical lines represent the first, third quartile, as well as the median. Now, the actual thickness of this box doesn't matter. There is no meaning to that thickness. This is typically about as thick as it is. I wouldn't make it a square. Now that we have the box in place with the quartiles, we can draw our whiskers. We draw the first whisker down to our minimum value, which is 5, and then we draw our upper whisker to the value that hasn't been identified as an outlier, and in this case it's going to be 65. The final thing we need to add to it is a star to represent the outlier, which is 85 in this case. And folks, what we have here now is a completed box plot. And this is fantastic because we can start to understand, based upon percentages, what we're looking at. Remember that we're creating box plots based on quartiles, which means that the first quarter of the data is between 5 and 15. The second quarter of the data is between 15 and 22.5. But then the last half of the data goes from 22.5 all the way out, including the outlier, to 85. This is now going to hopefully start to give you a picture of exactly what the data set looks like in terms of a distribution. Because what I see here is a skew to the right. And how do I know that? Because that outlier is creating this tail on the right-hand side. You can also tell based upon the median's position relative to the box, because the more divided up your data set is in terms of quartiles, if they are equal in quartiles, that's going to represent more of a symmetric distribution. So your ability to take a box plot and interpret it according to shape and according to outliers, fantastic. And we also have a center and spread in this case because we have the median and the interquartile range. So now we have two sets of different tools that we can use to describe center and spread. And the question becomes, why do we use certain ones over the others? And the answer comes from your understanding of the shape and if outliers are present. In short, if something is symmetric, that means that the values deviate about the same amount to the left or right of the mean. That also means that without outliers, there's no particular value that's drawing the mean one way or another. But imagine a data set where we count 1, 2, 3, 4, 5, 6 million. Well, obviously the value 6 million is going to have a significant effect on the actual calculated average of that data set. And that would also determine a much higher standard deviation because of the mechanics by which it's actually calculated. You use the mean in the calculation. But imagine using the median and interquartile range to describe the center and spread of that data set. Well, in that case, the actual magnitude of that value 6 million isn't going to move the center one way or another because we simply rearrange the values and we count in from the side until you get to the middle. So if you have an understanding of the mechanics of how these quantities are calculated, then the answer is, if the data set is symmetric and the shape is symmetric, you're going to use the mean and standard deviation to describe the center and spread. But if it is an obvious skewed data set, the better choice is going to be to use the IQR and median, because outliers and extreme values are not going to affect their quantities when you actually go to calculate them. So it's important that you always plot your data so that you understand what kind of distribution you have. But it's important that you understand more so the mechanics of how the mean, standard deviation, median, and interquartile range are calculated so that you can better understand why outliers cause these changes. In short, we say that medians and interquartile range are resistant to outliers. So in general, we are now equipped with the tools that we can use to begin to understand how to deal with a statistical problem. And we have some graphs that we can create, and we have some numbers that we can calculate. But now the big step that you're going to have to make is understanding, what do we do now? How do we take a scenario and understand the process by which we go from understanding the question to calculating the values to understanding what conclusions we can make? There are 4 steps in all statistical problems that I'm going to want to make sure that you always think about when we're going through them. State, plan, do, conclude. And what does that mean? State is simply asking, what question are we trying to answer? And this is going to go from rudimentary type things like, what is the probability of something happening? To, what is the significance of the difference of these two quantities later on in the course? The plan is going to be validating whatever choices you're about to make as far as the calculations are concerned. If you're going to use a particular statistical test, if you're going to use a particular measure of center, you're going to want to make sure you justify that here within the plan. The do is going to be the nice part, because that's going to be all the calculations and all the tools that you just learned in this chapter. It's important to recognize, though, that the do component is a very small component in the overall understanding of a statistical problem. So don't get fixated on the mathematics. I'm sure you've noticed by now, statistics certainly has math, but it is not a classic mathematics course. And finally, we have the idea of conclusion. And from this, we take the evidence now that we've gathered from our statistical analysis to try and make some sort of meaningful statement that may extend to a population or may have some sort of real-world setting. Maybe it's an experiment, and we've done some mathematics to determine that indeed a certain medication improves our ability to heal or something like that. So conclusions are fantastic because of all the work that comes before, hopefully sets us up to be successful in the way in which we can conclude if something is statistically significant or not. So next up, you're going to learn about the most important distribution in all of statistics, which is the normal distribution. And we're going to get into this idea of exactly what that is, how to use it, and how all of these tools can be beneficial to you moving forward. Best of luck with all of your practice problems, and we will see you again.